Let's introduce a bit of notation to talk about this, because we've already got tons of notation to talk about derivatives, right? We don't have any to talk about primitives, right? So usually we would say, if you've got some function f of x, okay? And if you were to differentiate it, say, take the derivative, okay? What's our standard way? What's our notation for that? F dash x, right? Okay. But what if, you know, we don't want to start from here and then differentiate. We want to start at something else, okay? And then say, well, what is its primitive? Okay. Now, I don't have good notation for anti-differentiation so far, and I don't want to introduce this other stuff to do with integration. Okay. So if I were to anti-differentiate this, right, what's it going to turn into? Generally, the most standard way to write it is to say, well, f is little, right? So where did it come from? Something bigger, right? So they use a capital. Okay. Now it's not equal, right? If I'm anti-differentiating from this side to this side, the derivative's over here. Does that make sense? You see that? So capital F is our standard way of writing down what's a primitive. Okay.
What if we wrote fx as like I usually write my fx.
Okay, yeah, all right. So now in some ways, I mean, it's just letters, right? So we could make it mean anything, yeah? And you know, in the past, when we were talking about polynomials, we're like capital P of x. We do that all the time. We don't make it, you know, lowercase p. Okay? So in some ways, it doesn't matter. However, because it's such a well-recognized convention, like textbooks are going to use it, exams are going to use it. If you've been using capital so far, I'm going to sort of encourage you to stop doing that and try and distinguish between, okay, this is usually the derivative and this is usually the primitive. Okay, is that all right? Okay. So we start off with an easy example, x squared and 2x, okay? But let's try and start to generalize this rule, right? We know our general rule for differentiating stuff with powers, right? So if I've got x to the n, yes? What do I do? What is the process of differentiating? What do I have to do? The power comes out the front first, right? And then I reduce the power by 1. Okay, so far so good. Now, if I were to go the other way, okay, so I'm trying to find out if f of x were that, what is its primitive? Okay, so let's remember this again. The two steps you did were bring the power out and then reduce by 1. Yes? So if I want to go in the opposite direction, I should do all those steps, but I should do them in exactly the opposite way. Does that make sense? Okay. So, instead of bringing the power out the front and then reducing, okay, remember you've got to do it exactly backwards, okay? So the first thing I'm going to do is increase the power, okay? Now can you see why I'm increasing the power first? It's because here I increase the power last. I'm trying to turn it upside down, exactly. And you'll see why there'll be a problem if you don't, right? Then here I multiply it. So what should I do now? I should divide. Okay. Now, I'm almost done, right? Yeah, this is a whole family, right? This is a whole bunch of different functions that would satisfy this. So I'll chuck that constant on the end. Now, let's just verify, does it work? Does it work? So, yeah, I'll use red, okay. So, going back to lowercase, it's sort of like saying capital F, but differentiate, okay? Doesn't work, let's do it longhand. Well, usually what do? I bring the power out the front, right? And then I reduce the power by 1, which will leave me with n. This denominator is still here. The constant becomes 0, right? Sorry, looks like a 6. That's a 0. Yes? So it looks like it checks out. That's fine, okay? So can you see, if you did it the other way, right? If you divided first and then increased the power, then this wouldn't work, right? You'd be off by a factor, okay? All right, so let's see if we can do some examples. Now here's the tricky thing, because we took a process that you're very familiar with, right? And then we just turned it on its head, we made everything backwards, okay? you will find, particularly at the beginning, that you confuse these two, right? You'll be like, am I meant to do differentiate or am I meant to integrate? Okay, sorry, anti-differentiate, right? They're very similar to each other. So just watch out. See, I'm doing it too. Let's have a column for the derivative and a column for the primitive, okay? And we'll do a whole bunch. Okay, so we already did an easy one before. 2x is going to turn into x squared plus c. We already noticed that, but can you see how it works with this rule? Okay, my power goes up to 2, and then I divide by that power, 2, which is what gets rid of the coefficient, and that's why it's just on its own. Okay. Well, how about multiplying it through by 5? What difference will it make? Okay. Well, let's put the work in here, even though I know you probably could do it in your head, right? But I'm going to put the power up, so 10x squared, and then I'm going to divide through by the power, right? Which leaves you with just 5x squared, which makes sense. Sorry, plus c, which makes sense because this is 5 times bigger than that, so you'd expect this to be 5 times bigger than this, which it is. Okay, how about, say, x squared? Push the power up, and then divide, right? Lost my constant. Okay. How about x to the power of, let's do the square root of x. Square root of x. Now, because we're trying to think in terms of, just like with differentiation, if you saw this, you're like, I want to put this in terms of something to the power of something. So this is x to the power of a half. Yes? Yep.
Can we turn it into 3x to the power of 3 on 2 over 2? Plus c.
Let's do the steps, okay? First thing is I'm going to increase the power, right? So increase it by 1, makes it 3 on 2. Yes? Now I take that power and I divide through. So that's dividing by, what's your brackets there? 3 on 2, right? Plus your constant. Now dividing by a fraction, that's a bit gross. So let's put those numbers where they belong. Okay. How about this? Okay, exactly the same. You increase the power by 1, and then you divide by the new power. No props. Plus my constant. Okay. Okay, how about this one?
One. How does that work? 1 plus c.
Uh-oh! What happened? Okay, now, why did it break? My rule was going so well.
Because you can't differentiate x to 0. Because really? Can you?
It's a horizontal line or something.
Well, you can.
Boom!
Thing.
Hold on a second. Hold on. Now stop for a second, right? What are we trying to do? We're trying to go from a function, this is our derivative, right? And say, well, where did it come from? What do you differentiate to get to that? What's the primitive?
Wait, is it undefined because c can be any number, and because there's no x in it, it can be any number?
Now, what is this function? Now, I wrote it in a sneaky way. I wrote it just like these ways, right? A normal way to write it would be 1 on x, right? Well, hold on. What's the thing you differentiate and you get to 1 on x? The natural log, right? Remember that one? Plus your constant, of course. Okay? Because when you differentiate log x, a different rule takes over, right? Sort of different. It takes you over to 1 on x, right? So, we should update this a little bit, right? This rule was doing really well. It was really even working for weird numbers like this, okay? But it broke down here, okay? So what do I need to say over here? This rule is not always true. Mr. Lowe's looking for you. Let me see what this is. Okay? This thing here is not always true. You don't always simply increase the number and then divide through. Right? There's a case where it stops working. What's the case?
-1. When the power is negative.
Now, will it work for other negative powers?
Yes.
How could we be sure? How about x to the minus 3? Okay, let's go through the steps. What do I do first?
X to the minus 2.
Increase the power,
Minus 2.
and then divide through by, okay, and the minus, I suppose I should put that on the top, right? Plus my constant. Now, how can I know if I'm right or not? I differentiate, right? Okay. Keep in mind, don't just, this is one of the great things about this topic, okay? Unlike, say, perms and columns, okay? You can know when you're right or wrong here. Because you get some result, and you can verify it immediately by differentiating, okay? And you can see, all right, what am I going to have to do? This minus 2 is going to come out the front, and then I'm going to reduce the power. You do end up at x to the minus 3. It's fine. So the only case where it stops working is where n is minus 1, because it becomes something different entirely. Okay? So then this is true where n can't equal minus 1. Okay? Does that make sense?